Dear students, in this session, we will see the behavior of real gases, how they are different from ideal gases, and what are the equations, and we will also see the compressibility factor. See, as I already told, the real gases are those gases which are present around because ideal gas is just an imaginary gas. So, all the gases which are around us are real gases. The behavior might change to different extent. And these real gases, they show deviation from ideal gas behavior, especially under high pressure and low temperature, because at this stage the intermolecular force of attraction comes into picture. Molecule will start attracting. They may undergo liquefaction. So they experience intermolecular forces, either attraction, repulsion. They have finite volume. So the volume of the particles of real gases cannot be neglected. They occupy certain volume and they approximate ideal behavior only at low pressure and high temperature, because under this condition they are far away from each other, so the forces of attraction is negligible and their volume is also negligible because the volume of the container comes into picture. And these real gases don't obey the ideal gas equation, which is PV equal to nRT. They obey this van der Waals equation with the correction terms A and B. So P plus A n square upon V square into V minus Nb equal to nRT. So where N is the number of moles, if N becomes 1, then it will be reduced to P plus A upon V square into V minus B equal to RT. So if you see this graphs where PV by RT is plotted against pressure, this one shows the difference from ideal behavior. So these real gases, you can see PV by nRT equal to 1. I mean PV, when PV is equal to RT, so PV by nRT will become 1. So this is the line which is applicable for ideal gas, and these are the lines which are applicable for various gases like hydrogen, nitrogen, oxygen, ethene and carbon dioxide. You can see they show considerable deviation from the ideal gas behavior. Especially some gases like carbon dioxide and ethene, so they show sudden dip right in the beginning and then they start approaching the ideal gas behavior, but again it will show positive deviation. Okay, that's mainly because of intermolecular attraction and also the molecular volume, which is not negligible. So this can be described in terms of the separate factor that is called compressibility factor Z. Z is ratio of PV to RT. So you know PV is equal to nRT for ideal gas. It's the ideal gas equation. If PV is equal to nRT, then PV by nRT should become 1. But it happens only for ideal gases. For real gases, this can be lesser than 1 or greater than 1. If it is lesser than 1, then those gases have higher force of attraction than the expected. If it is greater than 1, then the forces of attraction is lower or there can be repulsive force. You can see it here. Some gases like carbon dioxide, methane, all these, especially if you look at carbon dioxide, shows a sudden dip. What does it indicate? When you increase the pressure, volume suddenly decreases. So if that happens, then what happens? What does it indicate? It indicates that the liquid or the gas like carbon dioxide can be liquefied faster compared to these gases. Because there will be more force of attraction between the molecules of carbon dioxide. Carbon dioxide, when you increase the pressure, it will start becoming liquid. But it doesn't happen with all these gases. Nitrogen, hydrogen and helium, they show positive deviation. So what does it indicate? The positive deviation indicates these gases have, when you increase the pressure, they don't suddenly become liquid. You need high pressure. So as long as this higher temperature and lower pressure is maintained, they may show certain ideal behavior. But when you increase the pressure and start decreasing the temperature, they make considerable deviation from the ideal behavior. Certain gases have Z is lesser than 1. It indicates the forces of attraction between the molecules will be higher. Certain gases have Z is greater than 1. It indicates forces of attraction is very low or forces of repulsion between the molecules is considerable. So these are some of the references book, and these are online resources which you can refer. Thank you for watching.